So last time we talked about pulse code modulation, right? And we saw how to digitize messages using quantization followed by encoding, and also looked at the kind of quantization noise that we have to cope up with when we do pulse code modulation, right? Under the simplifying assumption that we use a uniform quantization, we also obtained an explicit expression for the signal to noise ratio, signal to quantization noise ratio, that we will be having to work with, having to cope with in a PCM system. And under the assumption that the signal also has a uniform distribution over the same interval for which your quantizer is designed, we found that a nice rule of thumb for predicting the performance of a PCM system is that for every additional bit that you introduce in your representation, you get a 6 dB advantage in signal to noise ratio, right? Because your SNR in dB is given by 6n, right? So that's a good rule of thumb to remember, even when your underlying signal that you're trying to quantize may not be uniform, right? It gives you a good idea of what kind of performance you can expect from a given PCM system of a given number of levels. Now, towards the end of the last class, we talked about the possibility of using a non-uniform quantizer, right? That is, in which the levels are not equally spaced but have a variable step size. And the motivation for that is that many real life signals that we actually deal with are not really uniformly distributed in a finite interval. They may be having a finite range, all right, but they may not be uniformly distributed over that range. Typical situation is that lower amplitudes are more likely than the higher amplitudes, right? So if, for example, a Gaussian distribution is a very commonly encountered distribution of signals that we deal with. There are other distributions too, but Gaussian is one of the most commonly used models for many signals. And in such a situation, it makes sense to have quantizer levels distributed non-uniformly over the range of values of x, right? We discussed that last time. In particular, we would like the levels to be the various quantization levels to be more crowded in that region where there is a high probability of the signal value lying, right? Whereas we like to space them out more sparsely towards the tail of the distribution where the probabilities of signal levels associated with those amplitudes are much smaller. One can actually obtain an optimum set of values for these boundaries x1, x2, x3 and the actual quantization levels m1, m2, m3 by suitably optimizing with respect to this distribution so as to maximize the signal to quantization noise ratio. However, we will not go into those details here. Perhaps we can take up one or two such problems in our extra class lectures or tutorials, whatever you like to call them. And at the moment, it is sufficient to take note of this fact that non-uniform quantization can give us significant advantage, and one can optimize it in this particular way. Now, since there can be a large variety of signals to deal with in practice, and one may not know a priori in a particular communication system what kind of signals you are going to deal with, what kind of probability distribution function you may have to work with, it also makes sense to design a quantizer which may not be optimized for a specific distribution. It should be kind of robust towards variations in the distribution, right? Because in reality, it will never be the case that you know a priori that you are always going to deal with Gaussian signals. Maybe it is not exactly Gaussian distribution, it's some other distribution, right? So therefore, even though one can optimize this kind of thing, you can choose you can design an optimum quantizer by appropriately selecting these xi's and mi's. It actually makes more sense not to optimize too much for a specific distribution, because your distribution is likely to change from time to time. What is more important is to have some kind of a robust quantization which is going to give a reasonably good performance over a fairly large variety of distributions, right? So we'll talk about these two issues in particular. First, the manner in which this non-uniform quantization is usually done. Instead of doing things in the way that are as depicted in this diagram, what is typically done is that you go through a process of compending. So non-uniform quantization via compending. Let me try to tell you what we mean by compending. Compending is a two-step process. It's in the first step, and that is done at the transmitter, you carry out what is called sample compression. And the first three letters of this word, COM, actually come from the first three letters of this word compression. Or perhaps the first four, perhaps, right? It may be, I think it's the first three. All right. And this is at the transmitter followed by a uniform quantizer, uniform quantization. So what we are saying is that instead of doing a non-uniform quantization with levels which are separated by variable steps from each other, you do an equivalent thing, somewhat equivalent thing, but first compressing the range of the amplitude of the input signal, right? And then follow it up by a uniform quantization. Now, this compression, I'll just illustrate this idea by a diagram. This compression is usually achieved by a transformation y is equal to g of x, right? So it's a memoryless transformation of a kind which compresses the amplitude range of the signal into a finite region, right? The higher amplitudes are also compressed to lie within a fixed dynamic range. So this is a typical nonlinear distribution that is used, nonlinear function. And this function should be chosen in such a way that y, what kind of random variable should y be? Should be uniformly distributed, right? Because if you are going to follow it up with uniform distribution, the motivation is that we expect this y to be very close to uniform distribution, right? So this g is chosen so as to make y nearly uniformly distributed, if not exactly, right? In fact, I'm sure you are aware of transformations which will render a given random variable x into another random variable y which will be uniformly distributed. You must have done that in your probability theory course if you have done a course in probability theory, right? And we can take that up separately as an exercise to remind you what kind of transformation is that, right? There are transformations, if you know what kind of distribution x has, from that knowledge you can obtain a transformation G such that y has uniform distribution. And since y has uniform distribution, you can now use a uniform quantizer. It makes sense to use a uniform quantizer. And that's it. As far as x is concerned, effectively you are carrying out a non-uniform quantization, right? This is best illustrated by means of a picture which I have here. This function that I got here represents your output y from the nonlinearity, and therefore this corresponds to g of x. All right. As you can see, a large dynamic range of x is being compressed into a finite dynamic range of y, going from y sub min to y sub max. So this is one end of the boundary and this is the other end. And if this G is appropriately selected, we can expect this y to be uniformly distributed, right? Do you remember what kind of G would give rise to?
G should be logarithmic.
G should be?
Logarithmic function.
No, actually depends on the distribution function of x, right? The most general form of G is if x has the cumulative distribution function fxx, then you can use this function as a memoryless transformation, where capital Fx is the cumulative distribution function of the random variable x. This is just to recapitulate for you what you might have done. If you haven't done, don't worry about it.
But
Okay.
sir, how can we realize CDF, this fxx?
Well, there are many ways of realizing this in practice these days. If nothing else, you can always realize any kind of function by a read-only memory, right? Any kind of memoryless nonlinearity can be a priori programmed into a ROM, and depending on the value of x, which can serve as the address of the ROM, you can obtain the value of y. It's very easy to do these things these days, so one doesn't have to worry about its analog implementation. Even that's also feasible, but digital implementation is extremely simple and convenient to work with. All right.
Could you give an example of an analog device which in general can manipulate or?
Well, they are as somebody mentioned, you can use a logarithmic amplifier, and many of these amplifiers will be very close to this kind of a distribution, these log characteristics. In general, actually, that is of academic interest because we will very rarely use such a precise distribution. Then for reasons which I have already just mentioned to you, because we don't want to optimize our quantizer for a specific distribution. We would rather have a nonlinearity G which is more robust and can work across a larger class of distributions, right? So that's really of academic interest.
So after choosing this fx of x, how do you choose G after that?
G is fx, right? Because that's very easy to show that if y is equal to fxx like that, then this y would always be independent of what fx is. Y would always be uniformly distributed. This is a very standard result in probability theory which you can check up or we can discuss separately. Now after having obtained y in this manner, you can do a uniform quantization over y. Have uniform steps. This picture doesn't exactly show uniform steps, but they should be across y. And effectively, as far as x is concerned, you are obtaining non-uniform quantization, as you can see, right? These are the steps correspondingly for the x, right? If you do uniform quantization across y, you are effectively achieving non-uniform quantization across x, right? Of course, this process will introduce distortion for the signal, right? Because y is equal to gx is not a linear function, so you are distorting the signal. There is a nonlinearity being introduced in the signal. In fact, the process of non-uniform quantization itself is equivalent to introducing some kind of a distortion. But this is very specifically obvious from here that if you do the non-uniform quantization in this particular manner, we are going to introduce deliberate distortion at the transmitter, which is not good. So what you have to do therefore is make sure that this effect is compensated for at the receiver, right? So as to remove the distortion. And therefore at the receiver you carry out an inverse transformation, G inverse y, alright, so as to obtain x, to undo the effect of this distortion. And that obviously would be, this inverse function would obviously expand the dynamic range of the signal, expand the range of the signal. So therefore what we have to have at the receiver is the opposite of this compressor, and obviously we can call it an expander, and it is from this combination of compression and expansion that this name companding is derived, right?
Explain this expander part again.
the expander is the inverse function which you must have, which you must implement at the receiver so as to undo the nonlinear operation that you did at the transmitter, which otherwise would introduce distortion for you, right? Any kind of nonlinearity will distort your signal. For example, what are the kind of things that you're familiar with nonlinear operations may do to the signal? Can you name a few?
Harmonic.
It will introduce intermodulation terms, right? If your, for example, signal has only a single frequency component, it will introduce multiple frequency components. It will generate additional frequency components which were not originally present in the signal, right? If you have more than one frequency components, then you'll get all kinds of sum and difference terms of those frequency components also introduced after the nonlinearity, which you don't want, right? So therefore, you must undo the effect of this distortion that you're deliberately carrying out from the point of view of a good quantization at the receiver by introducing an inverse function, which obviously would be some kind of an expander. It will be the inverse of this function, right? Mathematical inverse of this function, right? Which would be an expander. And using these terms, we get the term companding, right? So non-uniform quantization in general is done through the process of compression at the transmitter, followed by uniform quantization, and at the receiver we have to compensate for the compressor characteristics by having an expander, appropriate expander. Okay, I think that's sufficiently clear.
So you talked of dynamic this thing compression
Yes.
at the transmitter, like the thing adjusts itself with respect to the incoming signal.
One can do that, but it's usually more convenient to have a robust quantizer than optimum dynamic quantizer. For one thing, it is simpler to implement. One can standardize it, and for another thing, it gives you nearly as good results. Okay.
So sir, what do you mean by a robust this thing?
I'll just talk about that. By a robust quantizer, I only mean the fact that it should be distribution free. It should not depend that much, characteristics, its performance should not depend that much on the specific distribution with which it is faced in practice. Okay?
It's going to have a constant function like
I'm just coming to that. I'll give you some specific functions which are used typically in such robust quantizers. Now, typically the compression characteristics and the expansion characteristics have been a subject of wide study in the PCM literature during the early stages of development of PCM, and people try to look at various kinds of compression and expansion characteristics, and out of a lot of research, a lot of it was theoretical, but finally a set of laws have been given which have more or less been adopted as standards for use in PCM systems. One of these is called the mu law compression. Mostly these use logarithmic function, as somebody pointed out, which makes sense. It makes a lot of sense. And the other is called the A law compression. These specific laws are the culmination of a lot of studies in this area, both theoretical as well as experimental and empirical. So I will not be able to give you a justification for it here for lack of time as well as context. It will digress us quite a bit, but just mention what kind of laws these are. This mu law compression is what is normally used in the European continent. So most of the European standards, PCM standards, have the mu law compressor.
Mu law is in America and Japan. And A law is in Europe.
Maybe I have got the thing other way around. I'll have to check up on that. If you are very confident, maybe it's that way. My impression was that mu law was the continental and A law was the North American. But I may have got it the other way around. I don't remember these things very well sometimes. We'll have to check on that. But let me give you what these are. Good, somebody at least has heard of it and knows better than me. What's that? Speak out, no problem. These names have actually no significance. They only come from the fact that somehow this parameter mu was used in this expression and it's just known as mu left from that point of view. They are both logarithmic functions, log functions. Okay, that's a Mueller compression. And the Euler one relation is slightly more complicated. They look atrocious. Okay. So they're basically some complicated looking mathematical expressions which, as I said, have come out of a lot of study, both empirical as well as theoretical, and the main reason why they have been adopted as standards is that both these laws yield an average quantization noise which more or less is independent of what kind of signals we are feeding them into. Right? So that is what I mean by being robust. Right? The quantization noise that they introduce to some extent does depend on the signal that is being quantized, but the variation is very, very small. Okay? And therefore in that sense they are robust. It's better to use such laws or such nonlinearities than specifically design optimum nonlinearities, even if they can be made dynamically adaptable, right? Because they are more complicated to deal with. And this, in fact, these standards are now absolutely taken for granted. Many of the codecs, so-called codecs, coder decoders, which do the PCM transformation of a voice signal that are commercially available, would be available with these options, either Mueller compounding or Euler compounding. They are available in IC forms.
Even they can be varied for.
In fact, they have also been optimized more or less. For example, mu is typically taken to be 100, and so is A. Right? So that is about non-uniform quantization. Any questions? Anything about non-uniform quantization?
So the inverse function of these.
Yes. They will be quite complicated, and I haven't got them here. Okay. Let me now get into the system aspects of PCM system, typical PCM communication systems. The transmitter we are now quite familiar with. At the transmitter, the things we need for a PCM system are, to start with, we have a message empty which must be low pass filtered. I have not shown the low pass filter here, but that has to be there because this is immediately going to be followed by a sampling operation, and to make sure that there is no aliasing distortion, you must make sure that your sampling rate and low pass filter bandwidth are properly matched. Right? Alright. Typically for voice signals, this low pass filter will have a bandwidth of less than 4 kHz, and the sampling will be done at the rate of 8 kHz. This is followed by the quantizer and the encoder, and typically these two are realized as one block. typically known by the name of analog to digital conversion, right? This quantization process and encoding process are really slightly indistinguishable at the implementation level. They go more or less hand by hand. And as I said, in speech signals, we use typically 7 to 8 bits of quantization, which brings us to a data rate of, if you use 8 bits, 64 kilobits per second, right? Because your sampling rate is 8 kilohertz, each sample is being represented by 8 bits. So the final rate at which you have to transmit this data is 64 kilobits per second. And that's the standard PCM data rate, 64 kilobits per second. If you are going to do voice transmission over a digital channel, you will require a 64 kilobits per second line, right, or bandwidth corresponding to that. Now this is transmitted onto a channel which is usually noisy. It introduces noise, and to take care of this noise at the receiver or the repeater, this diagram could be that of the receiver at the final destination or of the receiver which is used at the repeater for requantizing the signal and retransmission. So this receiver diagram will be more or less same. Now, to take care of noise, you use at the front end what is called a matched filter. We'll talk about the need for a matched filter and its characteristics at a slightly later time in our course, but broadly at this time it is sufficient to appreciate that the main purpose is to be able to make correct decisions regarding whether in a particular bit interval a 1 or a 0 has been transmitted or received, because this decision is a non-trivial decision to make, because this pulse that is coming along with a lot of noise. It may not be obvious from the noisy signal, which is very weak, to immediately see whether it contains a 1 or a 0, right? To be able to make a good decision, you do a certain kind of processing on the received signal, which processing is known by the name of matched filtering.
That will be sort of noise based, filtering of the noise.
Yeah, the purpose is to remove the noise and to get a sample value based on which you can make a decision more reliably, right, depending on the output of this match filter, right? But we'll go into the details of that problem slightly later. At the moment, you just have to know that such processing is required to take care of noise. All right. Once you have got that done, then you can take a decision whether 1 or a 0 was transmitted, and then follow it up with a D to A converter. These bits are collected and put into a D to A converter, and that output is usually a quantized version of the input signal, and therefore you low pass filter it and finally get your estimate of the transmitted signal.
So what is that in the A2D converter, sir?
D to A converter.
A2D converter, what is the relation?
Mathematical formula.
Just a second, one question at a time. What is your question?
The A2D converter, is the relation of MT.
Oh, okay. I just got some notations here. This MT is the original signal, M sub S is the sample signal, M sub Q is the quantized signal, right, which is the sum of the sample signal plus an error term, the quantization error term, E sub Q, right. This is at the output of the D to A converter, you have an estimate of the quantized signal, and finally after low pass filtering, again you get an estimate of the original signal MT. So this, because first of all there could be still some noise that has trickled through, and more importantly your quantizer essentially introduces steps, staircase kind of thing, which you again remove by smoothing it out. Whatever error the quantizer has introduced, the quantization noise has also a broad spectrum. You remove as much of its energy as possible from the band of interest.
Repeater also converts it using LCA. And then
Followed, if it is a repeater, this will be again followed by a quantizer and encoder, sampler, quantizer and encoder. All right.
So
But usually, usually at the repeater level, one can just clean up the pulses and retransmit rather than carrying out the process of D to A conversion and low pass filtering, right? Because basically you have to still just retransmit. Good. Let's go into these things a little more in detail, although I think it is probably not necessary. I'm sure you know how A to D converters are typically implemented. This is a block diagram of a to D converter, which I'm sure you can recognize. What kind of A to D converter is this?
Ramp type.
Ramp type. What does it do? You have this sample signal which is held, and this is compared just as this sample is being generated. You also give what is called an encode command to the converter, which initiates the generation of a ramp signal. This incoming sample is compared with this ramp output, and when this exceeds this, the comparator output generates a signal which becomes a stop signal for the binary counter. And as long as this ramp is operational, this binary counter, this encode command also comes to this binary counter. This binary counter is counting from 0 onwards, right? And the moment this level is exceeded, the counter is made to stop counting, and the output of the counter now represents this level to which this ramp has reached, which also represents the level of the input signal, and therefore this becomes a binary representation of your digital signal, which is converted into a serial form and transmitted as PCM. That's the essential difference between a normal A to D converter and a PCM system. Normal A to D converter output is in parallel form, because typically it is going to be used in a machine with all the bits available, where all bits are required to be available simultaneously. But on a line, you have to transmit these bits in a serial mode, right? So the essential difference is that you need to have a parallel to serial converter for transmission onto a line.
What is the connection between sample and hold and the binary counter?
Oh, this clock is being counted,
Clock.
right? And the same clock is used for you may divide this clock somewhat, because this counter will be operating at a higher rate than the sampling rate here. Those relationships are not very clearly given over here. I'm sure you can work them out yourself. In any case, this is something which I'm sure is not new to you. Do you want me to keep it there for some time? All right.
So, but RAM type A to D converter is slower than there are faster versions.
Well, the specific type of A to D converter that you shall use will depend on the rate at which you want to do things, right? If it is a voice signal, this may be good enough, but if it is a picture signal which you want to quantize at a very fast rate, maybe you require a faster A to D converter and a different kind of A to D converter, right? So this is just as an example. This is not to say that all the time you're going to use this kind of A to D converter. Technology has made available many different kinds of A to D converters, and you choose the most appropriate one, both from the point of view of cost as well as from the point of view of meeting your needs, right? Always it's a trade-off between cost and what you can live with. Okay, can I remove it now? At the receiver, this slightly more blown up diagram of the receiver, you have the match filter followed by serial to parallel converter and a D to A converter, which is essentially a resistor network, resistor weighting network, followed by an operational amplifier. Now the important different thing here is this thing here, this block, which I have not talked about so far, but which is very crucial to any digital communication system. And this is the complexity. This in fact makes the digital communication receivers much more complex than corresponding analog communication receivers.
Sir,
the need for synchronization.
Synchronization is there in analog also, so DSB, SC, etc.
That's all. That kind of synchronization is also needed here. We'll see that later,
So this is
right? Well, this synchronization is slightly different. The kind of synchronization you're referring to in analog communication is basically that of the carrier, right? We'll need carrier synchronization here also when we use a carrier, right? But remember what we were doing in the process of encoding. We were taking a sample, putting them into a group of bits, and these bits were transmitted, right? Now at the receiver, you don't know where a particular word starts and where it ends, right? So you require synchronization at the word level, right? So as to demarcate different groups of bits from each other. Clear? And you also require synchronization at the bit level. You need to know precisely where each bit starts and where each bit ends, so as to enable the match filter to do its job properly, right? Because the match filter has to remove noise for a particular pulse, so as to enable you to make a correct decision whether in that bit interval a 1 or a 0 was transmitted, right? To be able to make the decision correctly for that bit interval, it must know where the interval starts and where it ends, right? So the match filter requires that information. Of course, usually if you have good bit level synchronization, it's very easy to derive the corresponding word level synchronization, because you know how many bits constitute a word, right? But you may still require to know precisely where the boundaries are, right? So for which one has to do additional things which are slightly irrelevant to the basic job of communicating information. For example, you may like to transmit some kind of a preamble, right, for the synchronizer to get ready. Some protocols have to be involved so that your receiver is set up to receive the information when it is transmitted.
Start stop bits or something.
There are various kinds of protocols. We'll talk about them at an appropriate time.
So, preamble.
that is
A preamble word, some kind of a protocol.
That is something which is done only at the beginning of the transmission. That's it, or something?
That's right. Something only at the beginning of the transmission, or something which may be done periodically if your channel is bad and you may like to set up the receiver again and again, right? So that's a slightly blown up picture of the receiver. Any questions on this? Okay.
So what is the synchronizer? What is the,
I just
how
talked.
is it implemented?
Oh, at the moment we are only looking at the block level needs. We'll be going to details of many of these things later, right? Because they will be required in many other contexts rather than just the PCM context. Now we come to an important question which was raised by somebody last time. We have looked at two different methods of converting or representing analog information by into a digital form, right? Namely the delta modulator and the PCM. And it makes sense to ask the question, how do they compare with each other? How do I know which one I should choose, right? I do know that delta modulator is a simple thing to implement, and in fact it doesn't have anything like word synchronization necessary for it to be at the receiver, because we just can, the demodulator is extremely simple. Much more than the modulator, the delta demodulator is extremely simple. All you require is an integrator and a low pass filter, no synchronization problems, right? Except that you have to take care of noise somehow, but that's something that can be done. So on the one hand, it looks like delta modulator may be a better option from the point of view of system complexity. But before we jump into conclusions, we must also see what kind of performance we can get from delta modulator for similar situations. And let's therefore look at the quantization noise in delta modulation. So we are now returning again to delta modulation, having understood PCM. let's do a bit of analysis here. Let me represent my the signal mt, which I am now quantizing by delta modulator, as sum of two components, m tilde t plus E sub qt, where this represents that staircase approximation that the delta modulator generates, right, of the mt. Remember, what does delta modulator do? Effectively, it gives us a sequence of binary pulses from which we can generate a staircase approximation of mt, which I am representing here by this notation. Okay, and therefore this represents the error of representation at time t. So E sub qt is nothing but mt minus m tilde t. And of course, magnitude of this will be always less than or equal to delta, where delta is a step size in the absence of slope overloading. If there is slope overload, then this error can become large, right? So this has to be qualified. This will be less than this only in the absence of slope overloading. Okay, now to be able to obtain the quantization noise for this case, we will have to make some assumptions, and one assumption we like to make is that that the PDF of E sub qt is distributed, its magnitude is less than delta. That means its value lies between minus delta to plus delta. Right? You can have minus delta, or you can maximum you can have on one side minus delta, on the other side plus delta. Is that okay? So we'll assume that the PDF of EQT is uniformly distributed over this range, right? And this is supported by observation in practice for many kind of signals. So assume to be uniform. Therefore, if I make this assumption, I can write expected value of EQ square t as 1 by 2 delta, which is the distribution of EQ, distribution function, density function of EQ, right, multiplied by E square, EQ square or E square d, which will be simply delta square by 3, right. If you evaluate this integral, the value will turn out to be delta square by t. Now, fortunately for us, not all of this noise is what you will finally hear after demodulation. Why?
LPF.
Because there is an LPF whose bandwidth is going to be governed by the signal bandwidth. If your signal has a bandwidth W, you are going to put a low pass filter with that bandwidth, whereas this noise will be some kind of a broadband noise, because this is having very fast fluctuations, right. This error signal is undergoing very fast fluctuations, so it's essentially some kind of a broadband noise. In fact, experimentally it is observed. Can I remove this sheet if you have written all these things down? Experimentally, this is an experimental observation of regarding the power spectrum of this noise. That E sub qt has a fairly constant kind of power spectral density function between 0, that is DC, 0 frequency, and Fs, F sub s, where F sub s is a sampling rate or the clock rate used in the delta modulator, right. So it has a power spectral density function which is nearly uniformly distributed over this range. Fs is your sampling frequency. That is, if I write the power spectral density function of E sub q, what will it look like? Its total power we know, delta square by 3, right? We just computed that. This power is uniformly distributed over this band of frequencies, right? That is from minus Fs to plus Fs. So it will be delta square by 6 Fs for this region and 0 elsewhere. Okay. How much time we have? Okay. Just I'll derive this expression. We'll do the discussion of this result next time. Therefore, now if you consider the noise n sub qt, which is coming out of the low pass filter in the demodulator, so this I'm distinguishing between the noise that is generated by the process of delta modulation and the noise which is finally observed after demodulation, after low pass filtering, right? So n sub qt is the let's say the response of the low pass filter or the baseband filter to this EQT. Right? The input is this noise along with the signal. The output is being represented by this noise. Essentially the two are going to be different in the frequency domain in the fact that this has a bandwidth equal to W, whereas this has a bandwidth given by Fs, right? This is the essential difference between these two noises.
In this case, the bandwidth will be Fs by 2.
No, Fs.
No, for the second one. For the
No. You remember
signals.
our sampling rate in delta modulation is much larger than the Nyquist rate, right? So there is nothing like Fs by 2, right? It is going to be much less in fact, right? It will depend on the signal bandwidth W, because the low pass filter must pass the signal. That's the main requirement. Baseband signal must have a bandwidth corresponding to empty, right? And usually Fs is now going to be much larger than 2W, right? In delta modulation, much larger, as I mentioned last time when we discussed delta modulation. Therefore, your expected value of n sub q square t is essentially going to be the energy of this noise or the power contained in the noise in the bandwidth from minus W to plus W, which is very easy to evaluate. Is delta square by 3 into W by Fs. Okay. I think we'll have to stop here and we'll start from this point next time.